Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the grand tapestry of scientific thought, certain threads possess a structural integrity and generative power that fundamentally alter the pattern of all subsequent inquiry. These are the conceptual breakthroughs that create new vocabularies for describing the universe, transforming what was once intractable complexity into elegant, solvable problems. Within the domain of probability theory, a field dedicated to quantifying uncertainty, the early 20th century was a crucible of such transformation. The prevailing paradigm, forged by giants like Bernoulli, de Moivre, and Laplace, rested upon a foundational pillar, the assumption of independence. The flip of one coin had no bearing on the next. The outcome of one roll of the dice failed to influence its successor. This was the world of the central limit theorem and the law of large numbers, a world of beautiful mathematical symmetry, but one that bore a limited resemblance to the richly interconnected fabric of reality. It was into this landscape that Andreyevich Markov, a formidable member of the St. Petersburg Mathematical School, introduced his 1906 paper, Extension of the Limit Theorems of Probability Theory to a Sum of Variables Connected in a Chain. This work, at first glance a highly technical generalization, was in truth a quiet revolution. By introducing a simple, powerful model for dependence, Markov unyoked probability theory from its classical constraints, providing the grammar for describing sequential phenomena from the diffusion of gases to the very structure of human language. This chain was more than a mathematical object, it was a new way of seeing, a tool that revealed the predictable rhythms hidden within the apparent chaos of dependent events, and in doing so, laid a cornerstone for much of modern science and technology. The genesis of Markov's 1906 paper lies deep within the intellectual soil of the Russian mathematical tradition, particularly in the work and influence of his mentor, Pavly Chebyshev. The Chebyshev school was characterized by a focus on concrete problems, a preference for analytic and algebraic methods over purely geometric intuition, and a relentless drive to establish the most general conditions under which major theorems held. Chebyshev himself had made significant strides in moving beyond strict independence, proving a version of the law of large numbers for sums of variables that were merely uncorrelated or weakly dependent. His methods, especially the powerful technique known as the method of moments, provided the essential toolkit that his students, Markov and Alexander Lyapunov, would inherit and refine. However, Chebyshev's framework for dependence was abstract and lacked a clear, generative structure. It quantified the decay of correlation without providing a specific model for how that dependence arose. A profound intellectual rivalry with Lyapunov further catalyzed Markov's efforts. The two mathematicians engaged in a sustained and sometimes acrimonious debate over the precise conditions required for the central limit theorem to apply. Each sought to prove the theorem under the weakest possible assumptions, a contest of rigor that pushed both to the frontiers of probabilistic thought. It was in this competitive environment, driven to find a class of dependent variables both general enough to be interesting and structured enough to be analytically tractable, that Markov conceived of his chains. His motivation was quintessentially pure mathematics, yet he possessed the foresight to understand its potential applications. This is perhaps best, if somewhat eccentrically, illustrated by his later application of the theory to the sequence of vowels and consonants in Alexander Pushkin's poetic masterpiece, Eugene. This endeavor, while seeming esoteric, was a profound statement, a demonstration that the tendrils of mathematical law extended even into the cherished domain of literary creation, suggesting a universe governed by discoverable principles. The work itself, Extension of the Limit Theorems of Probability Theory to a Sum of Variables Connected in a Chain, introduces a concept of startling elegance and profound consequence. The core innovation is the formulation of what is now universally known as the Markov property, or memorylessness, for a sequence of random variables, say x sub 1, x sub 2, x sub 3, and so on. This property asserts that a conditional probability distribution of a future state, for example x at step n plus 1, given the entire history of past states up to x at step n, depends solely upon the present state, x at step n. In formal language, the probability that x sub n plus 1 equals some value j, given that x sub n equals I, x sub n minus 1 equals k, and so forth back to the beginning of the sequence, is identical to the probability that x sub n plus 1 equals j given only that x sub n equals. The past influences the future exclusively through the present. All the information relevant for predicting the next step is encapsulated in the current position of the system. This simplification is the key that unlocks the analysis of dependence. The chain is the sequence of these variables, linked by transition probabilities. For a system with a finite number of states, these can be organized into a matrix, the transition matrix, where the element in the if row and jth column gives the probability of moving from state I to state j in a single. Having defined this structure, Markov's monumental achievement in the 1906 paper was to prove that the foundational limit theorems of probability theory could be extended to these chains. Specifically, he established a form of the law of large numbers for them. He demonstrated that for a certain class of chains, those that are today called ergodic, the system exhibits a long-run stability. Ergodicity, in this context, implies that a chain is irreducible, meaning it is possible to get from any state to any other state, and aperiodic, meaning it does not get trapped in deterministic cycles. Under these conditions, Markov proved that the proportion of time the chain spends in any given state converges to a unique, fixed value as the number of steps approaches infinity. This limiting value is independent of the chain's initial state and corresponds to a unique stationary distribution. This stationary distribution, often denoted by the Greek letter pi, is the probability distribution that remains unchanged after the application of the transition matrix. The proof strategy he employed was a direct inheritance from his mentor, Chebyshev. Using the method of moments, Markov painstakingly calculated the expected values of powers of the sum of the variables in the chain. He showed that these moments converged as the length of the chain grew to the corresponding moments of a Gaussian, or normal, distribution. This was a technical tour de force, requiring immense algebraic dexterity to manage the dependencies between terms, and it definitively established that his chains obeyed a central limit theorem, solidifying their status as a natural and powerful generalization of independent trials. The immediate impact of Markov's work was largely confined to the elite echelons of the St. Petersburg mathematical community. It was recognized as a brilliant piece of analysis, a significant victory in the ongoing intellectual joust with Liepunov over the boundaries of the central limit theorem. Its applicability, however, was demonstrated almost immediately within the realm of physics. In 1907, a year after Markov's paper, the physicists Paul and Tatiana Ehrenfest proposed a simple model for heat diffusion, now known as the Ehrenfest model, in which particles move between two containers. This model was a perfect, and likely independent, rediscovery of the concept of a finite-state Markov chain, illustrating its profound physical relevance. Markov's own demonstration, published in 1913, involved his infamous analysis of 20,000 letters from Pushkin's Eugene. By treating the sequence of vowels and consonants as a two-state Markov chain, he calculated the transition probabilities and showed that the stable, predictable nature of the chain mirrored the statistical regularities of the text. It was a powerful, if slightly whimsical, proof of concept that established a link between abstract probability theory and the structure of natural language. The true flourishing of Markov's idea, however, occurred decades later, as its seeds were planted in fertile new fields. The evolution of his work traces a direct lineage to some of the most important technological and scientific developments of the 20th century. In his seminal 1948 paper, A Mathematical Theory of Communication, Claude Shannon, the father of information theory, explicitly used Markov chains to model the statistical structure of English. He conceived of language as a stochastic process, where the probability of the next letter depends on the preceding ones. His engram models a higher-order Markov chains, a direct extension of Markov's original idea, and they form the conceptual basis for modern natural language processing, from predictive text on smartphones to machine translation. The computational age provided the ultimate playground for Markov's chains. The PageRank algorithm, which was the foundational technology behind the Google search engine, modeled the entire World Wide Web as a colossal Markov chain. In this model, the states are web pages and the transitions are hyperlinks. A random surfer clicks from page to page, and the stationary distribution of this massive chain assigns an importance score to each page, the very page rank itself. The long-run proportion of time a surfer spends on a page becomes its measure of authority. The applications continued to proliferate across disciplines in population genetics to model the drift of allele frequencies in chemistry, to describe sequences of chemical reactions in finance, to model credit rating migrations, and, with significant caveats, market states. The theoretical framework itself was also deepened and generalized. In the 1930s, Andrey Kolmogorov, another intellectual heir of the Russian school, placed Markov's work on a rigorous measure-theoretic footing. Kolmogorov's axiomatic formulation gave rise to the theory of continuous time, Markov processes and processes on general state spaces, transforming the chain into a foundational element of the modern theory of stochastic processes. The very elegance of the Markov property is, of course, also its primary limitation. The assumption that the future depends only on the present is a profound simplification that fails to capture many real-world phenomena exhibiting long-range dependence or complex memory structures. Financial markets, for instance, often display behaviors like volatility clustering. where periods of high fluctuation are followed by more of the same, a feature at odds with a simple Markovian model. The weather, while possessing some Markovian character, is influenced by vast, slow-moving systems that impart a memory far longer than a single day. Yet these critiques served as creative pressures, fostering further innovation. The recognition of these limitations led directly to the development of more sophisticated models. Higher-order Markov chains, where the next state depends on the previous k-states, were a natural first step. Hidden Markov models, or introduced a powerful new layer of abstraction, postulating an unobserved, underlying Markov process that generates the observable data, and have become an indispensable tool in fields like speech recognition, where the observed acoustic signal is modeled as being generated by a hidden sequence of phonemes, and in bioinformatics for gene finding. Thus, Markov's original concept served as a robust foundation upon which more elaborate and realistic structures could be built. His legacy is shaped by the very critiques his work engendered, a testament to its foundational importance. Furthermore, understanding Markov the man provides a richer context for his creation. He was a committed rationalist, and a vocal critic of the Tsarist autocracy and the influence of the Orthodox Church. Some historians compellingly argue that his work in probability was an extension of his philosophical worldview, a desire to demonstrate that even phenomena attributed to chance, free will, or divine providence were subject to mathematical law, in proving that a sequence of dependent variables converges to a predictable, stable distribution. Was making a subtle but powerful argument for a universe governed by cause and effect, where order emerges from the probabilistic interaction of its. In retrospect, and in Markov's 1906 paper, did far more to extend the limit theorems. It introduced a paradigm shift in scientific modelling, providing a bridge from the idealized world of independent events to the interconnected, sequential reality we inhabit, by defining a tractable form of dependence, the Markov property. He armed future generations with a tool of unprecedented versatility. What began as a highly specialized inquiry into the convergence properties of a sum of variables became the intellectual bedrock for information theory, modern search algorithms, computational biology, and countless other fields. His chain binds the analysis of Pushkin's poetry to the ranking of web pages, a testament to the unifying power of a deep mathematical idea. The world it describes is one where the past is not forgotten, but its influence is carried forward, distilled into the single, potent moment of the present. Markov taught probability theory how to remember, and in doing so, he provided a language for understanding the intricate dance between randomness and order, a language that continues to reveal the hidden logic of a world connected in a chain.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.